Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list published on October 6, 2025, about 2 days ago. This paper introduces AInstein, a controlled framework that probes whether large language models can generate valid research solutions from pre-trained knowledge alone, finding that models often rediscover feasible approaches and craft novel, valid alternatives, yet their problem solving is fragile and sensitive to framing. The paper is titled AInstein, Assessing the Feasibility of AI-Generated Approaches to Research Problems. And as we'll see later, the implications for autonomous scientific discovery are quite significant. It uses a two-phase generalizer and solver with iterative critique loops, scoring 214 ICLR papers via a large language model judge on success rate, rediscovery, and novel and valid, with targeted manual checks. Alright. Figure 1 outlines the AInstein workflow that tests reasoning by turning a scientific abstract into a problem and then a proposed solution. The diagram highlights two critique loops that act like fast self-review and slower external review, which push the solver to revise until the proposal is solid. The left block shows the generalizer converting the abstract into a solution-blind problem. The right block shows the solver cycling through critiques and stopping when happy, yielding a rediscovered or novel solution. So Figure 1 sketched the workflow. Table 1 compares the full ICLR dataset to the curated set and shows intentional oversampling of higher quality tiers. Oral papers make up about 17%, spotlights contribute about 31%. Posters account for roughly 51%, while rejected and withdrawn are omitted. The curated total is 214 items, which supports fair testing across tiers because the sample emphasizes accepted work. Well, Figure 2 shows that the quality checks for the problem generalizer move together in predictable ways. The deficit score means a combined penalty for how much the distilled problem degrades, and it rises when information loss or ambiguity increase. This correlation matrix, a grid that shows how measures co-vary, highlights strong links to those two factors. The result supports using the deficit score because it captures the main failure modes. Okay. Table 3 reports how solver success changes under lenient versus strict evaluation. The key message is that the internal model strength drives outcomes, with the GPT-OSS-120B setup leading across problem sources. Rediscovery drops sharply under the strict threshold because the judge demands functional equivalence, which means the proposed method must match the original in function. Novel and valid stays roughly stable, showing that alternative, scientifically sound solutions remain common even when exact matches fail. Okay. Figure 3 compares model performance across oral, spotlight, and poster tiers and shows a stable ordering. The strongest internal agent, GPT-OSS-120B, leads on all axes because the critique loop lets it refine proposals more effectively. Results are plotted as radar charts, which display scores around a circle for each tier. The strict threshold tau equals 5 still leaves the ranking unchanged. Alright. Two takeaways stand out. Strong internal critique drives success, while perfect rediscovery under strict checks is rare, yet models often produce novel and valid alternatives. The broader implication is clear. Autonomous scientific assistants are within reach, but reliability hinges on careful framing, stronger reasoning training, and rigorous evaluation. Thanks for listening. That is it for this episode of the AI Research Roundup. I am Alex.